All stars grow and change throughout their lives. Some stars explode at the end of their lives, and we call those explosions supernovae. This happens to stars that are very large, much larger than our Sun. Our Sun, which is a medium-mass star, will instead eventually discard its outer layers, exposing just the core. This core is small, hot, and bright, and roughly the size of the Earth. We call it a white dwarf. White dwarfs don't explode, unless they eat too much and gain too much mass. An explosion like this is called a Type 1a supernova. When white dwarfs explode, they always give off about the same amount of light, and this means that we can use them to measure distances in the universe. Just as distant streetlights look dimmer than ones closer to us, distant Type 1a supernovae look dimmer than nearby supernovae. This is how we can work out distances. When astronomers used this technique, they found some very interesting information about the universe. They discovered that the expansion of the universe hasn't been slowing down since the Big Bang, but speeding up.
A massive object is dropped into the ergosphere of a Kerr black hole on a carefully tuned trajectory. If the object is split into two pieces at exactly the right point, one half will go plummeting through the event horizon, while the other is ejected from the ergosphere and escapes. In fact, it escapes with more kinetic energy than it had coming in, up to 20% of the energy that was bound up in the mass of the half that was lost. This energy is extracted from the rotational energy in the ergosphere, slowing the black hole's spin. To get more technical, it works because the weird space-time flip in the Kerr metric of the ergosphere allows one half of the object to acquire negative energy, which is transferred to the black hole, while the other half gains the difference in energy as kinetic energy. So there's your black hole engine. Maneuver rocks into a Kerr black hole, blow them apart at the right time, and catch the kinetic energy of the pieces that get ejected. Sounds a little messy actually, but you can do this with light. Light that is directed through the ergosphere in the direction of rotation will also extract rotational energy and emerge amplified in a process called superradiance. This way, the rotational energy can be extracted with, in principle, 100% efficiency. Oh, and you can also build a black hole bomb this way, by surrounding a Kerr black hole with mirrors. Then you just shine a flashlight at the black hole, and its photons pass through the ergosphere again and again and again, becoming exponentially amplified, until boom. The last process we'll talk about is actually important in the real universe. It's the Blandford-Znajek process. In this case, you have a magnetic field produced by the flow of material around the black hole in an accretion disk. The flow of space in the ergosphere spins up the magnetic field into a gigantic particle accelerator. Charged particles are accelerated along those magnetic field lines and can radiate intense light. Ultimately, the energy of that light is extracted from the rotational energy of the black hole. It's hypothesized that some jets observed from accreting black holes may be powered by this process.